Hello, this is Mr. P, and today we're going to learn about the graphs of the sine and cosine curves. Before we actually go through the graphs, I want you to see how they are generated. These functions are called circular functions because their geometric meaning has to do with circles. So if we look at a unit circle, such as this one here, then the input to the sine function, we'll talk about the sine function first, the input is going to be the angle. So you can see as I open up my terminal side here, the positive x-axis will be the initial side, this will be our terminal side, and this will be our angle theta. As we open up our angle theta, the physical interpretation of the sine function is this blue segment here. It's the length of the segment. So the input is an angle, the output is the length of a segment. That is the geometric meaning. And we can see in quadrant 1, we start out with a 0-degree angle. We have no blue segment there, so it starts out at a value of 0. As our angle gets larger, we see that the length of the blue segment gets larger until it reaches a maximum value of 1. The length of the blue segment would be this radius, and that is the largest that value is ever going to get. As we continue to get a larger and larger angle, we go into the second quadrant, and the blue segment starts getting smaller and smaller until it gets back down to 0 when it gets to an angle of pi. So at pi over 2, which is 90 degrees, we have our maximum value. Once we reach pi, we have, again, the 0 value, which was that intercept. And then as we get an even bigger angle, we can see now our segment here, which is a directed segment, and it does have direction, so it starts going negative. So it continues going negative, more negative, till it hits the angle 3 pi over 2, which reaches the minimum value of -1. And then as we go into the fourth quadrant, it continues to get less negative until it gets up into 0 at 2 pi. From there, if you go even further of an angle than 2 pi, it's just going to continue that cycle over and over. That's why they call these functions periodic. As it goes through the next rotation of the circle, you're going to get all the same y values along the way. And that pattern from 0 to 2 pi is repeated over and over. And we can see that in the actual graph. We start out within the period, which is 2 pi, that is one revolution of the circle. We start at a 0-degree angle and end up at an angle of 2 pi. Within that one revolution of the circle, we hit all of the possible values. We start out at the intercept, we go up to the maximum value, back to the intercept, down to the minimum value, and back to the intercept. Notice how the maximum and minimum values are +1 and -1. That's why the range of this function is positive or -1. But the domain is all real numbers, because we can put in any value of theta into the function and get back a value for that function. But that value for the function will always be between -1 and 1 within that channel. Now when we graph these, we're going to take a parent function approach. We're going to look at the characteristics and the shape of this parent function, and then use our transformations to apply that to any equation involving sine or cosine. Now, some other properties to realize is that the sine curve is an odd function. That doesn't mean it's weird. That means that it has symmetry with respect to the origin. And two ways you can look at symmetry with respect to the origin. You can either look at, if we take this first cycle of the curve, from 0 to 2 pi, we call that the cycle. If we take that and reflect that horizontally over the y-axis, you would have something that goes like this. And then if we reflect it vertically about the y-axis, or flip it upside down, it would coincide with the graph on this side. So symmetry with respect to the origin means you can reflect it horizontally and then reflect it vertically, or reflect it vertically then horizontally, and you're going to end up with the same graph. Another way to look at origin symmetry, and the reason it's called origin symmetry, is if you take any point on the graph itself and then draw the segment, a straight line segment to the origin. So if I choose this point here and draw a segment to the origin, if you extend that segment the same direction in the same distance through the origin, you will arrive at a corresponding point on the graph, another point on the graph. So it doesn't matter what point we take. If we take this one, draw a line segment to the origin, and then continue that the same distance, we will get another point on the graph. That's why it's symmetry with respect to the origin. Now for our parent function approach, we're going to graph one cycle of the graph by looking at the 5 key points. And these are those 5 key points. For the sine curve, we start at the intercept. We start in the middle, basically. Then we're going to go up to our maximum value. Then we're going to go down to our middle, our intercept, down to our minimum value, and then back up to where we started. So notice how the left endpoint and the right endpoint for the cycle are always going to be at the same y value. And halfway between those is going to be that same y value. And then between the first 2 intercepts is the maximum, between the second 2 intercepts is the minimum. We're going to use that idea, and then if we need to move these around with transformations, we can do that. Now, speaking of transformations, we're going to actually look at the sine curve first, because the sine curve is really just the cosine curve is really just a phase shift of the sine curve. So if I take this and I shift it pi over 2 units, I actually get this curve right here. So we're going to see that the cosine curve is really just a shift of the sine curve. But also what's important to understand is the actual shape. A lot of times you will see the sine curve graphed like this, where you have from 0 to 1, and then from 0 to pi over 2 is the same distance physically when you draw out your axes. However, pi over 2 is 1.57. That is larger than 1. So this is really skewed from reality. This is really squished in or compressed horizontally. So although in most math books you're going to see it drawn this way, this is not the true shape of the sine curve. Because one of the things you'll find in calculus is that the slopes of these curves, or the derivatives, the slope of the sine curve is never going to get steeper than 1. And this slope here is a little bit steeper than 1 because it's compressed. If you look at the true shape of the sine curve, which is this one here, you'll see it's really a more stretched out curve than it's generally drawn. And it's perfectly fine to draw it this way as long as you understand the reality of the slopes here. You'll see the slope never gets steeper than 1 or negative 1. That occurs at the intercepts. Now, the period that we talked about, the left endpoint to the right endpoint, can really be any point on the graph to its corresponding point in the next cycle. That distance is the period. And the amplitude is the distance from the center to the top, or from the center to the bottom would be the same number. It's half of that range. And you can see here the true shape from the period to the amplitude has a ratio of 2 pi to 1, or tau to 1 if you like using that notation. As opposed to the way it's usually drawn, the period here is a 4 to 1 ratio physically, the way they have it drawn here, where in reality it's 2 pi to 1. So as long as you understand that this is the true shape of the function, then it's okay to not draw it to scale. Alright, for the cosine function, we're going to start out by saying that is an even function, which means it's symmetry with respect to the y-axis, so it has horizontal symmetry. If you take the graph and reflect it about the y-axis, you're going to get the same graph. You can see if we take this part, the bold part, and we flip it over the y-axis, we will still have the same graph. This is the same shape as the sine curve, we start at a little different spot. The left endpoint, rather than starting in the middle, starts at the maximum. So we start at the maximum, go down to the intercept in the middle, down to the minimum, back to the intercept, and then back to the maximum. That is our first cycle of the cosine curve. So for graphing, these are going to be the 5 key points. It's going to be the left endpoint and the right endpoint are both going to be at the maximum. Halfway between those will be the minimum point. And then halfway between the first 2 will be an intercept, and halfway between the second 2 will be an intercept. That's generally how we're going to graph these. Now we should first revisit the transformations, make sure we know how to do these transformations. If we take any of those parent functions, and this does apply to all functions, if we change the equation of the function, then that is either going to shift or stretch or compress or reflect the graph. And depending on where we make that change is how it's going to affect the graph. For example, if any changes you're making outside of the parent function is going to affect the graph vertically. And that is always going to happen. It's going to affect your y values. And it's going to be an intuitive case. It's going to do it exactly the way you would expect it to. If you're adding or subtracting, that's always going to be a shift, whether it's inside or outside. Adding or subtracting is always shifting. And multiplying and dividing changes the shape of the graph. But if you add or subtract outside, it's going to shift it vertically. And you would expect adding to go up, which it does, and subtraction to go down, which it does. Multiplying and dividing, you're changing the shape. You would expect multiplying to make it bigger, and it does. You stretch it vertically. And you'd expect division to make it smaller, and it does. You compress it vertically. And changing the sign, that's sign SIGN, or multiplying by -1, is going to be a reflection, and that reflection will be about the x-axis if you're doing it outside, because it is a vertical. Reflection about the x-axis is a vertical reflection. So any changes made to the equation outside of the parent function will affect the graph vertically. Any changes to the equation inside the parent function will affect the graph horizontally, but this is a counterintuitive case. You would expect adding to go to the right normally, and it's the opposite of that. It actually shifts it to the left, where subtraction would actually shift it to the right. You would expect normally multiplying to make something bigger, but if you're multiplying inside, then you're actually compressing it horizontally. And division you expect to make smaller, but you're actually stretching it horizontally. However, the reflection is what you'd expect. The reflection, because it's about the y-axis, is a horizontal reflection. So then again, any change made inside the parent function will affect the graph horizontally. All right, let's look at a quick example of this with the squared function. If we start out with y equals x squared, which is this parabola, then our first transformation is we're going to add 3 to the equation, and we're adding 3 outside of the parent function, so it's going to affect our graph vertically, which we can see when we actually do the transformation just shifts it up 3 units. That means any point on the graph is now shifted up 3 units to be on the blue parabola. So the vertex here went up 1, 2, 3 units, or even this point here goes up 1, 2, 3 units for its new corresponding points. Now we see the second equation, though, is different than the first one. Here we're actually adding inside the parent function. So this is going to shift our graph horizontally, but in a counterintuitive way. We sometimes expect adding to go to the right, so it's going to be the opposite of that, which means it's really going to shift 3 units to the left. So again, every point on the original graph, such as the vertex here, will go 1, 2, 3 units to the left for the new corresponding point. Now, if you want to get a technical explanation of why it's counterintuitive, since we're making our change inside the parent function, we're actually affecting the domain. We're changing the input. So in reality, we're actually shifting the plane itself 3 units to the right, which has the effect of shifting the graph 3 units to the left. All right, let's take a look at the procedure for graphing these sinusoidal functions. And they're called sinusoidals because the sine and the cosine are both really the same curve, just shifted. But we're going to look at them in the form of a sine of some expression. So we may or may not have a coefficient out in front of the function, and the expression can be, the argument can be an expression, not just a single variable. Plus we could have adding or subtracting outside, and we could have reflections. We want to pay attention to those as well. So there are 4 pieces of information that you're going to jot down a little side work before you actually make the graphs. The first one is the amplitude. If you remember, that's the distance from the center to the top or from the center to the bottom. You can easily get that just by looking at the equation. It's going to be the absolute value of that coefficient, the coefficient out front. So the absolute value of A is your amplitude. The period is the distance from the left endpoint to the right endpoint. It's the length of the cycle. And you can get that by thinking of the transformations. The period of sine and cosine is both 2 pi for the parent function. But then if we multiply inside, we're actually compressing it. So that's why you see the division here. That would be our transformation. So 2 pi divided by whatever the coefficient of x is, that's going to be your period. For left endpoint and right endpoint, you can use these equations, which is basically taking the argument, setting it equal to 0, and solving for x. Or a better way to think of it is the same question we've been asking ourselves all along: what is the value of x that causes something? So here, if we think of the left point as the value of x that causes the argument to be 0, then that would mean you can just set your argument equal to 0 and solve for x. Notice how if we add c to this side, to both sides, and then divide by b, we're going to get c over b as our left endpoint. And that's also known as the phase shift. It's often called the phase shift as well. For the right endpoint, you can take the argument, set it equal to 2 pi, or ask yourself the question, what is the value of x that causes the argument to be 2 pi? That is going to be my right endpoint. That's more of an algebraic interpretation, but you can also think of it physically as if you take the left endpoint and add the period to it, because the period is the distance of that cycle, then you're going to get the right endpoint. So notice how the left endpoint of c over b plus the period, 2 pi over b, that will give us our right endpoint, which also algebraically works out to be the value of x that causes the argument to be 2 pi. So 2 different ways you could look at that. All right, with all that, we should now be able to do some graphing. Let's start with y equals 1/2 cosine of x. So there's 4 pieces of information we're going to do for every graph before we graph it. First one is the amplitude. We're going to look at the coefficient in front of the trig function. So our amplitude is going to be 1/2. And that helps me to set my vertical scale. I don't want this first line here to be a 1, because then if I'm trying to plot a 1/2, I got to plot something in between there. So I want to, because the amplitude is only 1/2, I'm going to give myself a little room here, and I'm going to make this 1 and -1. That way I can easily plot a point of 1/2. Okay, our period is the next thing we need to know, and notice how there are no changes to the argument. It's just going to be the same as the parent function, so our period is going to be 2 pi. Or you could say, yes, the coefficient technically is 1, so 2 pi divided by 1 is 2 pi. But if you just notice it as no change from the parent function, then you know your period is 2 pi. Left endpoint, we want the value of x that causes the argument to be 0. Well, that would be simply be 0. And right endpoint, we can say the value of x that causes the argument to be 2 pi, which is 2 pi. Or you could say your left endpoint plus your period is your right endpoint. So either way, you're going to get 2 pi. And that helps me give me my scale here. I know I need to go from 0 to 2 pi, so if I went by quadrants, I would have 0, pi over 2, pi, 3 pi over 2, and 2 pi, and that would be my scale horizontally. And that's usually what my scale is going to be, unless we have some other fraction in here, a change to the period or something that would cause other numbers to work easier. All right, so once I have my scale, I have these 4 points. You also want to make a note if you have any reflections, which we do not, or if you have any vertical shifts, up or down, which we do not. So for our 5 key points, you want to recognize we do have a cosine graph here, so we're going to start at the maximum, and the maximum is going to be 1/2 because of the amplitude. So at the left endpoint, which is 0, our y value is going to be that amplitude. So this point is our first point on the graph. That's our left endpoint. Well, if you know the left endpoint, the right endpoint, it will be at the same y value. So if I know the y value there, I know the y value there. And for the cosine graph, those are the maximum points. So halfway between them will be the minimum point. That'll be at -1/2. Remember, the amplitude is up 1/2 or down 1/2. That gives us our range. Now, halfway between the first 2 points is our intercept, and halfway between the second 2 points is an intercept as well. Now, resist the urge to try to connect those with straight lines. This is not a absolute value graph. You want to draw a nice curvy wave through there, And when you connect the dots, this is what your graph is going to look like. Notice how that first cycle of the graph will simply repeat indefinitely. All right, so that's our first graph. Let's take a look at one more. We're gonna change the amplitude a little bit. This time we're gonna do the graph of y equals 3 cosine of x. So again, those same four points or four ideas we want to start with. First one being the amplitude, which in this case will be 3. It's the absolute value of that coefficient. So my amplitude is 3. Again, no change to the period because our argument is the same as the parent function, so the period will be 2 pi. Left endpoint, value of x that causes the argument to be 0, that's going to be 0. And the right endpoint, value of x that causes the argument to be 2 pi is going to be 2 pi. Or in other words, the left endpoint plus the period is the right endpoint. All right, for our scale, the amplitude's 3 this time, so I want to make sure I go up to positive 3 and down to negative 3. So I use that for my vertical scale. And for our cycle here, we're doing 0 to 2 pi, so I'm going to use the same scale as I did before. Quadrantal angles here, 0, pi over 2, pi, 3 pi over 2, 2 pi. And now since we're at cosine, we start at our maximum value. So at our left endpoint, we're going to have our maximum value. So that will be our point there, which means our right endpoint will have the same value. Halfway between them, we're going to have our minimum value, which will be negative 3. And halfway between the first 2 points is going to be the intercept, and halfway between the second 2 points is going to be the intercept. Those are our 5 key points. Connect the dots with a nice smooth curve, and that will be our graph. Notice how, don't forget to put the arrows on both sides because this curve does continue on indefinitely to the left and to the right. All right, so we did a couple of cosines. Let's go ahead and do a sine curve. We're going to look at y equals the sine of x over 2. All right, we're starting out with the same 4 pieces of information. The amplitude is the coefficient of the function itself, so that is simply going to be 1. The period is going to be 2 pi divided by the coefficient of x. Now x over 2 is the same as 1/2 times x, so the coefficient is really 1/2. 2 pi divided by 1/2 is the same as 2 pi times 2, which is 4 pi. So the period here is going to be 4 pi, not 2 pi. Notice how when we multiply inside or divide inside, we change the shape, which affects that period. For the left endpoint, we still say what's the value of x that causes the argument to be 0? That is going to be 0. The right endpoint, we say what's the value of x that causes the argument to be 2 pi, or even easier in this case, if you have your left endpoint plus your period, then your right endpoint is going to be 4 pi. Now for our scale, our amplitude's 1, so I'm going to use that, plus 1, minus 1. And I want to make sure I leave enough room horizontally so we get to 2 pi. And my graph is large enough here where I can go to 2 pi and 4 pi. This will be one cycle of the graph. Now since we have a sine curve, we're no longer starting at the maximum value, we're starting at the intercept. So at the left endpoint, we have the intercept we start out with, which means we're going to end with the intercept as well. The right endpoint will also be 0. Halfway between those 2 intercepts is another intercept on the sine curve. Halfway between the first 2 intercepts is the maximum value, which is 1. That's our amplitude. And halfway between the second 2 is the minimum value, which is negative 1. So we can see it really starts to take shape with those 5 key points, and draw a nice smooth curve through those, and that will be your graph. Now usually these 4 points are enough to graph everything unless you have a reflection or a vertical shift to pay attention to as well. And let's see what happens there. Here we have, oh actually that's going to be the next example. Here we have one more example where we put it all together. Here we have y equals 1/2 sine of x minus pi over 3. So we're going to approach the problem the same as all the others. With the amplitude is the absolute value of the coefficient, so that is 1/2. The period is 2 pi divided by the coefficient of x. and there is no coefficient of x, or in other words, it's 1. So 2 pi divided by 1 is just 2 pi. You only change the period if you're multiplying or dividing inside the parent function. Now our left endpoint, we're asking ourselves the question, what's the value of x that causes the argument to be 0? Well, that would be pi over 3. And I think here the easier way is the left endpoint plus 2 pi will give me the right endpoint. So the right endpoint is going to be 7 pi over 3. So for my vertical scale, I can still do the plus and minus 1, because for the 1/2 I can definitely graph those inside. And then for the horizontal scale, though, I'm not going to use quadrantal angles, because notice how my denominator here is 3. So these are all in thirds. So that would be an easier scale for me to use, I think. So I'm going to go 0, 1/3 pi, 2/3 pi, 3/3 pi. In other words, I'm going to make this one pi. So then we can go 3 more to get to 2 pi. Because our denominator is 3, it'll make it easier to have the scale in pi over 3, in thirds. So our left endpoint is going to be a pi over 3. This is where our cycle starts, not at the origin. And the sine curve does start out at the intercept, so that would be a point on our graph, which means at our right endpoint, which is 7 pi over 3, that's 1 more third than 2 pi, we're going to have the same value. Left endpoint and right endpoint always have the same value. So with the sine curve, halfway between those is another intercept. Halfway between the first two is our maximum value, which is 1/2. Now halfway between them would be right here, in between those two tick marks. So that would be our maximum value. Halfway between these two would be right there. That is going to be our minimum value. And once you have those 5 key points, you simply draw a nice smooth curve through them. Don't forget the arrows on each end, and you have your graph. All right, for our next example, we're going to have a negative sign on the outside. So let's see how we deal with that. Plus we have some other, the argument looks a little more complicated. So we're still going to take the same approach, though. We start with the amplitude as the absolute value of the coefficient of the trig function. So the amplitude is going to be 3. The period is going to be 2 pi divided by the coefficient of x. So 2 pi divided by 2 pi gives me 1. And if I look at the left endpoint, that is going to be the value of x. The value of x that causes the argument to be 0. And if you actually do the math there, that's going to be -2. If x is -2, then you'd have -4 pi plus 4 pi would be 0. And the right endpoint, the value of x that causes the argument to be 2 pi. But an easier way in this case would be the left endpoint plus the period is going to give me my right endpoint. So -2 plus 1 is -1. Now, we do have to also recognize that we have a negative sign on the outside, so this graph will be reflected vertically, and we have to remember that when we're doing our shape. In other words, we're going to start out, let's look at our scale though. Since our amplitude is 3, I want to make sure I have enough room to go plus and minus 3 vertically. So here's +3, -3. And our scale for left and right, I want to make sure I can fit my left endpoint. So I can't really make these lines each be worth 1, because then our left endpoint is -2. That would be off the left side. So I'm going to make each of these lines worth 2, and that would give me this scale here. And that way at least I can fit that first cycle in there. So starting at our left endpoint, the cosine curve would normally start at the maximum, but since we are reflecting vertically, we're going to start at the minimum. So at -2, which is our left endpoint, instead of being at +3, we're going to be at -3. So that'll be our beginning spot, our left endpoint, and the right endpoint will be the same y value. So at -1, which is right here, it's going to be the same y value. Now halfway between the two minimums is going to be the maximum, which would be a +3. So that would be this point here. Halfway between the first 2 points is an intercept, and we can see already things are getting a little tight. Halfway between these 2 points is going to be another intercept. And if we draw a smooth curve through those, which is a little tough to do, but if we do it, it ends up looking like this. We can see our graph because 2 pi is really 6.28 approximately. So we're really compressing our graph a lot here. That's why it looks so compressed horizontally. And I give you plenty of cycles here, more than just the first cycle, to see the periodic nature of this curve. All right, let's look at our final example. Here we have 2 plus 3 cosine of 2x. Again, we're going to start out with our amplitude is simply the coefficient of the trig function, so the absolute value of that, which is going to be 3. Our period is 2 pi divided by whatever the coefficient of x is, so 2 pi divided by 2 gives us a period of pi. Left endpoint, value of x that causes the argument to be 0, that would be 0. And right endpoint, value of x that causes the argument to be 2 pi is pi. Or in other words, left endpoint plus period equals right endpoint. And here there's one more thing to pay attention to. We do have the plus 2 on the outside. We're adding 2 to this function, so it's going to be a vertical shift of 2. So since we're dealing with a cosine function and there's no reflections, so we're going to start at the left endpoint with a maximum value. Now the left endpoint, which is, first we need our scale. If we look at our scale, I want to make sure I leave enough room so that I have a maximum value of 3 that's going to get shifted up 2 units, so we have to leave enough room to get a plus 5 or a negative 5. But since we're going up, we really care about the plus 5. So if I make that my vertical scale, then I can get a plus 5 there. Because at the left endpoint, that would be the maximum, which would be 3. But then we're shifting the entire graph up 2 units, so we're actually going to start at the maximum value of 5. Oh, and our horizontal scale is going to be our normal scale that we've been using. Now, if my left endpoint has a value of 5, then my right endpoint, which is at pi, will also have a value of 5. Halfway between those 2 points is going to be the minimum value, which would normally be a negative 3. Sorry. But then we're shifting that up 2 units, so it's going to be a negative 1. Remember, all 5 of these points are getting shifted up 2 units from what they would have been. So halfway between the first 2 points is what would have been the intercept, but then that's shifted up 2 units, so it's going to be at a positive 2. And halfway between these 2 is also going to be a positive 2. And now if I make a nice smooth curve through those 5 key points, I get what our final graph is, which looks like this. And this one you can really see the periodic nature. If we take the shape of these 5 key points, and then you see that shape is repeated indefinitely. All right, and we're done.